applied with either soft computing techniques or sometimes in data-driven techniques and with hard computing also. So let us read about what is hard computing and what is soft computing. To know about the hard computing, I just gave the example of first y is equal to mx plus c. This is nothing but a example equation of a line. When we want to plot a line, its equation is y is equal to mx plus c. So y is completely depend upon that x. If you do not put the value of x, if you do not have the value of x, then you cannot get the value of y. A deterministic kind of relationship, but yes, y is completely depend upon x. And if m is not known, x is not known, if you don't know the constant c, then you cannot place that line. That is what the hard, where the requirement of data is very, very compulsory. So many hard equations, numerical methods we have learned in our academics also. We use also many of the theoretical applications, theoretical approaches of different courses. We always learn so many numerical methods, numerical equations, wherein this hard computing is involved. Data and the equations, deterministic parameter and deterministic parameters, all are involved in that processes. But then the soft computing. If I say that I have account in bank and I want to withdraw the money, for that nowadays we use this Swift cards and all, but earlier we used to work with the checks. So if I do a sign on my check and if I submit it to that accountant officer or a bank officer, he or she always used to see that sign first. He recognized that whether the sign is perfectly matching with my original sign or not. He confirms that yes, this check is given by Pradnya Dikshit only by my sign. And every time I am not able to do the sign perfectly as it is the earlier check. Suppose I gave 5 checks in last 6 months to that accountant officer. Was it possible to work with that every time I would be able to give the check with a very perfect similar sign? No. Many a times we do have here and there in the words, and our signing style is a little bit different in every check. But still, that person recognizes us because it has some particular sign stored in his mind. Data is stored and it try to match the pattern recognition, try to match the pattern, but not hard and fast like a equation. It just see that whether it is matching or not, soft towards the data, not so hard towards the like the numerical methods or equations. It has the tolerance, targets the tolerance of the real world to partial truths, uncertainty, imprecision, inaccuracy in data in order to arrive at meaningful solutions. That is the concept of soft computing. An ideal concept of that soft computing is what? Ideal of that is human brain. Because our human brain works on this concept. Tolerance, data tolerance is also there. Every time we do not require so many perfections in our day-to-day activities. But yes, we recognize our friend, we recognize our friend's relative very easily by just observing the faces. And we never say that friend should tell me he is his relative or what. No, we recognize by facial expressions. We recognize by pattern recognition likewise. So it is soft towards, human brain is completely soft towards the data. It has that particular tolerance. And then it is able to take the decisions using the knowledge stored, earlier experiences. Likewise, soft computing also works with that. So what are the soft computing techniques? Neural networks, the technique which generally map any random input to the random output vector and try to give the meaningful solution. Fuzzy logic, multi-valued logic used to quantify the variables, then genetic algorithm, hybrid system, probabilistic reasoning. We should not go in depth with that, but yes, these are the soft computing techniques. Going ahead with that now. Neural network, artificial neural network is a soft computing technique. I hope now you have understood this. Say this is a very common example when we just do searching on a Amazon website. Earlier I have searched this website, and that is actually, it is showing my particular interest products. Earlier I have just searched on that, but see, hello Pradnya, it is giving the relative figures, relative informations on the same websites. This is what the AI works. It stores the information and it uses that whenever required. This is a simple example, but let us go the traditional examples so that we can understand how our brain works, how we learn, and how we can mimic it in our machines. Our grandmother or senior persons in our family, always they are able to tell us the perfect situation of a rainfall, early notification of a rainfall. Our grandmother just observes the cloud situations from the balcony or from the terrace, and she immediately sometimes gives the comment that today आज तो बारिश हो जाएगी, आज तो भारी बरसात हो जाएगी. How that it is? Because she has many such experiences stored in her brain, and she uses that particular knowledge, earlier experience, to right now, today she is using that entire knowledge and giving the decision that आज भारी बरसात होगी भैया. Likewise, and that comes true many of the times. How it is possible? Her brain, human brain, stores the knowledge, learns from the experiences, and use that experience knowledge wherever necessary, whenever necessary, to take the decisions, to solve the problems. Another very simple incident in our day-to-day life: by smelling a particular dish in our kitchen, even we do not see the particular dish which is going on in a actually kitchen, but by just smelling in an outside room, we can recognize that particular dish name. Oh, आज तो जलेबी बन रही है, आज तो कुछ पापड़ा और ढोकला चल रहा है, or other any other thing. But we recognize it because that smell, that particular smell was stored in your brain, in human brain. And when today again you just smell the same thing, you feel the same thing, immediately your brain recalls that memory, recalls that knowledge, and the decision is in your mind that yes, आज तो जलेबी बन रही है क्योंकि वही स्मेल है. Likewise, how it works? आपने तो देखा नहीं है किचन में जाके कि क्या चल रहा है, but still you recognize it very accurately because your brain works accurately on what? Earlier experiences. Likewise, when the small child is there, we always teach that small child that this is a cat. उसको पता नहीं होता है पहले से कि ये कैट है, एनिमल वो पहले देखता है. स्मॉल बॉर्न चाइल्ड, वेरी वेरी लिटिल चाइल्ड, इनफैक्ट वो जब देखता है तो इसको पता नहीं होता है कि ये कैट है. हम लोग उसे ट्रेन करते हैं. सो नाउ अ ट्रेनिंग वर्ड इज देयर इन आवर डिस्कशन. सी, योर ब्रेन लर्न्स. We provide training to that small infant that this animal is cat, and again before that, this particular letter called as a C, this particular letter is called as A, this particular letter is called as T, and when together we write all these letters, it becomes a particular word cat. Cat mane billi. Likewise, we train that particular infant. Human being learns from the training, from the experiences. And when in the next time when that child see that particular animal, then वो बच्चा छोटी आवाज में बोलता है, हाँ मम्मा ये तो कैट है. Like that, because he utilizes his knowledge, earlier experiences. Training was there in earlier mode, and now the child is given decision using the earlier knowledge, solving the problem right now, utilizing the information. Acquire and apply the knowledge. Intelligence is there. Now I will just give here some few numbers, and one or two from the audience, please give the answer for these numbers. Let me know from your side. It's 1, and next again the number is 1, next is 2, next is 3, next is 5, next is 8. Let me know the next answer or next number.
13. 12.
Very good. 13. Next one. What will be the next number? 13 is
23.
23. No.
21.
21.
21.
Yes, 21. Next will be 34.
34.
Yes,
34.
correctly. How you have recognized that? I have not told you any formula. I have not displayed any formula for this number series. It is a particular number series. Then how your brain has given this particular decision? How you have given these answers? Your brain has trained on these earlier numbers 1, 1, 2, 3, 5. When you recognize that 5 plus 3 is 8, 8 plus 5 is 13. Likewise, or some may give answer that this is Fibonacci series, madam, because we have learned in our 12th academic sessions. Because that is a Fibonacci series. Yes, you have recalled very correctly. Brain learns from past experiences, stored information, stores the data and uses it with when and when required. And that's why you have recalled your memories of numbers and the Fibonacci series, mathematics, all this knowledge is there. And so that you can do the addition, 13 plus 8 is 21. Likewise, you can just immediately reply the answer because your brain works with the data. Your brain is data driven. See, now we have again used different terminology, data driven. It is artificial intelligence. It is originally intelligent and it is data driven also because it works with the data. Whatever the data is stored in the brain, again, it works on earlier experiences. All these there in the brain. So can we use all these capacities of your human brain in machines? If we can do this artificially using machines or computers, this is nothing but the artificial neural network. But because whatever we have done this, whatever you have given the answers, actually your neural network works there and neural networks have given the answers, not you. So if the biological neural network is there in human brain, can we mimic its capacity in machines? Then it will be an artificial neural network. And this is the concept of artificial neural network. By definition, it is a massively parallel distributed information processing system resembling biological neural networks of human brain. That resembling biological neural networks of a human brain, just we have seen so many examples. And now, massively parallel distributed information processing system. Yes, it processes the information. Neurons processes the information. How? We will learn that. But this NN has different applications in all engineering field that we have seen. Again, I'm not going in depth with that. But let us have a look on biological neuron first. To understand the artificial neural networks working, first we will learn about the biological neuron. And you are observing here, let me take the pointer first. These are two cells, smallest cells in our brain. This is first cell and it is nothing but a smallest cell neuron. You are observing here the central nucleus. These are actually some tentacles like things which we know as dendrites. You are observing here a connection of two dendrites at one particular point and a junction or a dark dot is there which we call as a synapse. One particular long thread-like structure is there which is nothing but axon. This axon is again connected with another neuron here or there. Likewise, here is also this one is connected to this second neuron likewise. So we will concentrate on this particularly. A neuron, smallest cell. Here, from all the sides, all these dendrites, these carry the signals to this particular center of the neuron or at the cell or the cell body. Okay, how? We human being or human body have different sensors. Actually, we have sensing organs. By eye we can sense something, by skin we can sense something. Likewise, signals are processing. These are nothing but the signals. So signals are processing from different sensing organs to our brain, and that too particularly at this particular cell, a smallest neuron with all these dendrites. Okay, while coming to the information or processing this particular signal to this particular neuron, actually you are observing dendrites are coming from all the directions, and one or the other, a combination or connection of these dendrites are there at particular this particular dot junction, like a structure is there, that is nothing but a synapse. Synapse is nothing but connections of dendrites takes place. Then the further signal will process up to the center of this. Particularly if you are observing here, this is a nucleus center of that neuron, and around that, actually surrounding space of this center nucleus is but filled with some fluid which is known as neurotransmitter fluid. And neurotransmitter fluid and the central nucleus and all these dendrites, this entire includes with a small neuron. This is known as a cell body. So when the signal is processing from all the organs, sensing organs, to this particular actually central space nucleus, it has to travel from this neurotransmitter fluid. And if that neurotransmitter fluid is not there, then there is a difficulty to transform this signal towards this. So it should have always in that mind. If it is absent, then all of you must have seen a Hindi movie that I don't know whether you have seen or not, but I will just give one particular example. Munna Bhai MBBS. That was a Hindi movie, and in that the person just forgets every time whatever he knows, because this particular fluid was absent in that. So the information which is processing here, if you observe, it is gathered together in this cell body. Signals are coming together and in this cell body, and the summation of all the signals takes place. And further, this summation, if it is greater than one particular threshold value, one particular value, then the signal fires and then decision will be taken fast. Further, when the threshold signal is achieved, summation is greater than the threshold signal, signal is going to fire, and the information again, whatever the decision is here, after that summation, that decision or the signal is fired and the information will process again to the next neuron through this axon. And likewise, there are thousands of neurons connected to each other, which passes the information in further direction from one neuron to the other neuron, and these are parallelly connected. And how many neurons are there? If you just know, 10 raised to 11 neurons, 10 raised to 11 times. So it is a massively, so many neurons connected with each other in parallel connections, and they process the information. So it is said that massively parallel distributed information processing system resembling biological neural network of human brain. So if you can create such a network which is massively parallel, which can distribute the information like this brain, then it is known as artificial neural network. So massively parallel words are there. Now going ahead with this again. This is again flowchart what we have discussed right now. First, the signal or the impulse travels through the dendrites, that means the sensing organs, to the input receivers. Then they come to the synapse, then enters to the cell body, soma. Input signals combine. Combination of all signals takes place. Information is completely gathered. Signal used to actually fire. Then if the combination is strong, greater than the threshold value, then the signal will fire and the decision will be taken, and it will be passed further. Likewise, the same technique is just included here in an artificial neuron. You are observing this particular artificial neuron, a single neuron. These X1, X2, X3, these are actually the inputs which are giving the information to this cell body. And these are connected with these weights, W1, W2, W3. These are known as the synaptic weights. These are known as the synaptic weights. And the total information is processed up to the cell body like this. multiplication of this x1 w1, x2 w2, x3 w3. Again, all this summation, like we have seen in earlier images, that the total information is processed here in the cell body, and it should have some particular threshold value. The summation should cross the threshold value. That is what in our natural biological neuron. We are preparing this artificial neuron purposely to solve our problems, because artificial neural network, we are preparing our aim to prepare the artificial neural network or use the artificial neural network to solve one particular problem. So every time that signal should fire, this is what our basic need is there. So therefore, to every time signal should fire, we always add a bias in that summation. It is actually supporting some particular parameter information which is giving to the summation, and because of that the signal becomes stronger. Again, x1 w1 x2 w2 and addition of a bias, this is nothing but a summation. It passes through some transfer function f, and we receives the output y, required output in a required fashion. So this transfer function is playing again an important role here. See that we are never giving a particular equation to that. Output is received from this transfer function, and that can be in a form of 1 upon 1 plus e raised to minus sum. See, this summation, whatever the cell body is there, in that actually summation is taking place here, 1 upon 1 plus e raised to minus sum, likewise. Okay, so in this particular fashion, we in an artificial neuron, random input is mapped to the random output to get the required answer or required facility. So linking of such neurons in systematic way forms an artificial neural network. So this is nothing but a first neuron or a single neuron. If you link together, a network of these artificial neurons will be there, and that is nothing but artificial neural network. So you are observing here a typical architecture of ANN, artificial neural network. See how many neurons are connected now, inputs are there. In this input series, actually 1, 2, 3, 4, 5 neurons are there you are observing, and one is nothing but the last layer you are observing as the output. That means we have done one particular neural network in which 5 neurons are there in an input layer. Now the first, whatever you are observing, this actually layer is nothing but the first layer, input layer. This is the last layer, output layer, where one neuron is there, and you are observing this in between layer which is known as a hidden layer. So this is actually 5:3:1. One neuron is there in output. Let me just take the pen here so that I can explain. See it. This input information we have to pass on through the weights and biases. We will use the transfer function. Summation will be there for the information. Transfer function will be there. And then using the transfer function, information is processed and we will receive this output. This output is equal to 1 here. So this is the output layer. You can observe here. This is nothing but the input layer, and this is nothing but the hidden layer. Whenever we provide this hidden layer, we actually gives the more degrees of the freedom to that. See here, input 1, x1, x2, x3, x4, x5, 5 inputs we can give. Everywhere these synaptic weights will be there, w1, w2, w3. Each weight is again mapped with this or linked with this next neuron in the next layer. That means in a hidden layer actually. So I can write it here, h1, h2, h3. These 3 neurons are there. So summation information, this x1 w1, x2 w2, x3 w3 all, the product will be there, this weighted synaptic weights and the input product plus the bias will be added here. This total summation will be given here at this particular neuron. Transfer function will be used, and the output of that final product and addition it will be transferred using the transfer function, which is also known as the activation function. And again, the information is received at this particular end. Again, the output of this first layer, input to the hidden, this will be utilized as the input for the next layer combination. And the information is again processed in a similar manner to the output. Finally, again, bias will be added here, product of summation will be taken place, and the weights will be added. Everything will be done as in earlier case, and we will receive the output in the required fashion. So it is a information processing system using this transfer functions. Information is processed, and these inputs are connected or mapped to the output. So random input is mapped to the random output to get the reliable solutions. This is what the working concept of artificial neural network. As here, 5 neurons in input layer are there, 3 neurons in hidden layer are there, and 1 neuron is there in an output layer. This is known as 5 is to 3 is to 1 architecture of artificial neuron, artificial neural network. So this neural network can be expressed with this particular architecture, 5 is to 3 is to 1. Okay. Likewise, now we need to know how many inputs are there in our problem concept, what we exactly need to go with the output, why we are developing our neural network, for which particular problem you want to develop this particular neural network. Can we find out evaporation using this artificial neural network technique? Can we find out bearing capacity? Can we find out compressive strength of a concrete? These are civil engineering problems, civil engineering domain field, actually the concepts. Determination of compressive strength. Can we find out rainfall runoff relationship? Can we find out the discharge? Can we find out can we just do the forecasting of discharge, forecasting of temperature, evaporation using this artificial intelligence technique, AI technique, which is not completely based on the hard computing, but which uses the soft computing base and which can work on the data. See, in this entire information, we have not given any equation. Likewise, we know that Mayer's equation or Horton's equation for hydrological processes, infiltration and all, evaporation and all. We have not given any equation here, but we can just provide the information of measured data. If the data is there in your hand, domain knowledge is there in there with you, then you can design your own neural network to solve the domain problem. Okay, now going ahead with this, see how it works. This is a working explanatory figure of a neural network, how the information is processed to this layer, here particularly 2 hidden layers are there. This is the input layer and this is the output layer. 2 actually outputs are there. So architecture for this is 3 is to 4 is to 4 is to 2. So it is not necessary that every time you should consider one output. No, you can go with multiple outputs. But generally, all civil engineering kind of problems can be solved with only one hidden layer. One hidden layer is sufficient to consider all engineering problems. One output is also sufficient many of the times. But if you want to just develop or design a particular neural network with 2 or 3 or multiple outputs, yes, you can do that. That depend upon the problem statement and the domain knowledge again. So what here we are observing again, x1 into w1 plus the bias summation will be there, then the transfer function will be there. This total summation will be just pass it out from the transfer function and the information is processed up to this node. Then whatever the output we received here, again it will be passed further in a next layer considering again the same process. And again from here to here, and we will receive the output whatever we require. So here again, the concept of artificial neural network is explained. I'm not going in depth with the learning concept here. Now, how many types of networks are there? Here, as we have seen, first type is feed forward network. The information is processing from input layer to the hidden layer to the output layer in a forward direction only. So this is known as feed forward network. But if you are observing here in the right hand side figure, the information is going back again from this neuron to this neuron, output layer to the hidden layer to the input layer. So here it is known as a recurrent neural network. But many of the times this is not required in our applications. But yes, feed forward network is applied many of the times. Other network types are there: Cohen network, Hamming's network, radial basis network. But let us not go in depth with that because this is only a 3-hour sessions. We have to introduce artificial neural network to you students only, not in depth, and we need to go with the applications also. How this artificial neural network is used to solve the civil engineering problems, that is also our interest for this session. So let me just give you the information of transfer functions. Whatever we have said, that the total information collected in a summation plus the bias, it is processed further using this transfer functions. So how many transfer functions are there? The tan-sigmoid transfer function is there, which is known as tan-sig. Another one is hard limb transfer function, which is known as hard limb, right now here. Then next one is this Sattling transfer function, linear transfer function, radial basis functions, and log sigmoidal transfer functions. The data is transformed and the information is transformed using this particular transfer function. Information is activated using this particular transfer functions. And you are observing here different ranges of transfer functions also. -1 to 1, -1 to 1, 0 to 1, +1 to 1, likewise. So it always helps to process the information in particular fashion. We are not going in depth why we are using the transfer function in this particular session. Now, you will ask me that, yes, you are going to map random input to the random output, but where is the process of training actually? Where is the process of learning of this neural network actually? This neural network learns here when we provide the hidden layers, when we provide the weights, when we provide the biases. Actually, weights and biases are the elements which stores the knowledge, stores the information, and works with the data. Hidden layers are also the processes, so that these helps to give the information. Learning concept starts here when the iterative process starts. How the iteration will be? See, the information is processed here to here to here, and the output is received. Suppose I'm just designing this neural network to find out the evaporation. I have used here wind speed as one of the input parameter, then maximum temperature as the another parameter, and minimum temperature as the another parameter. So 3 inputs are there. Using the information of wind speed, maximum temperature, minimum temperature, my expectation is evaporation and transpiration both. I need to find these 2 outputs, final products, as evaporation also and transpiration also. Okay, to get these 2 outputs, my inputs are these 2. We are not providing any equation or any hard equation, numerical method to that. But we have provided this data. Now this data will processed through these hidden layers. 4 neurons you are observing, connection of the weights you are observing. So weights and biases, actually these are the very important parameters which stores the information, which helps to information processing system also. And then we are receiving particular answer here. Suppose my expected answer is 4 and neural network which we have designed, it has a given answer is 4. That means there is a difference of 5 minus 4 is 1. So the difference in actual required observed value or the measured value or the target value, we always say to that it is a target value. My target value is 5 and the answer given by the NN is 4. So predicted answer output is this. So target minus the output is the difference, or we may say that it is an error. So in a single iteration, I have received, suppose this particular one as an error. Now in the next iteration, the error should be minimized. So again, I will just pass it on this particular information back to the input layer. And this is nothing but a backward process. Feed forward back propagation process is also there. Using this particular method or a type of a neural network, we just find out, propagate the error back. In the next iteration, it will again reduce down. And while we train this all, these weights and biases get every time updated, or these weights and biases get improvised. As these weights and biases get improvised, your error will be every time reduced down. And we should do this iteration so many times or until we required the required minimum error in our neural network or the training process. This is how it learns and train. We can train the neural network in this particular fashion. Once it is completely trained, then finalized weights and biases we can use to test the neural network or whatever the developed neural network is there. For this, we should have some unseen data sets with us. Then and then only we can test our developed model. Otherwise, it is not possible. Likewise, in school teaching or in academic teaching, we teachers always provide some unseen numerical problems in your exam, and we test your knowledge. Similarly, we should have some unseen data package with us to test the neural network which we have developed. Okay, so network training is nothing but an iterative process or procedure to minimize the error between new network output and the target. For this, actually, we can do so many iterations and all. But this training can be with a supervised concept or unsupervised concept. In a supervised training, both input and output are required to give to your neural network. That means we should have input values also, we should have output targeted values also with us. Then and then only we can test and validate our network. Again, in unsupervised kind of a training, output is not required. It relies on the recognition of inputs into the clusters. Then whatever you have developed the neural network, it is very necessary to validate it. It involves the evaluating the network performance on a set of test problems, not used for the training. That means, again, our training data set should be different, validation data set should be different, and testing data set should be different. Okay? But for the validation data set, whose solutions are available for the comparison, this data set should be with you, but answers are always should be with you. Then and then you can able to do the validation. Okay. After validation, you can test your model, you can test your neural network with unseen data set. So this is what the neural network training. Now see it here, actually it is happening. Training is, you can observe here how the neural network is training. This neural network is with 2 is to 3 is to 1 architecture. Two input neurons are there, 3 hidden neurons are there, and 1 output neuron is there. But see, for every time these values of weights and biases are changing. That means for every iteration, actually, weights and biases are improvising. Mind well, we cannot change the input. Never. We can only change the weights and biases. Okay. Now, as the weights and biases changing, every iteration to iteration, you can see this number also. Right now, 59. Now again, 0 iteration, 10 iterations, 20 iterations. For every iterations, the error is reducing, and as the error is receiving at the lowest value, at that time, the performance here is the highest one. See, when this red line reaches up to the observed high peak, actually it is giving good performance at its best. The error is very, very low. So when the error is reduced down to the lowest level, definitely the answer will be increased. Answer will be improvised. So this is how we can train the neural network by every iterations. There are some training algorithms also, depending upon the first order local methods, second order methods, and global methods also. But the LM algorithm, which works on the Jacobian matrix and second order derivative functions. This works fastest one. This is a faster algorithm. Okay, let us not go to that, but you should know different algorithms of neural network. Now, there are some important aspects of neural network modeling. Network architecture means what? Data collection and processing, pre-processing means what? Initialization of the weights means what? Number of training samples means what? Stopping criteria means what? Validation means what? And data division means what? Let us see one by one. Network architecture, where we have just seen the example of a evapotranspiration 2 is to 3 is to 2, or 5 is to, let us take that, 5 is to 5 is to 1. One as the output, 5 inputs are there, one hidden layer is there, and in one hidden layer only 5 neurons we have considered. How to decide that? Depending upon the problem and the domain knowledge, you can decide this input and output combinations and architecture of a neural network. Number of neurons in input layer, it should be equal to number of model inputs. So जितने आपके पास मॉडल इनपुट्स होंगे उतने ही न्यूरॉन्स होंगे इनपुट लेयर में. Number of neurons in output layer, it should match with the number of model outputs. Number of hidden layers and number of neurons in each hidden layer. That is, we should go with a trial and error process or experience. By your own experience, you will learn to know how to fix the number of neurons and number of hidden layers. But generally, one hidden layer is sufficient for our engineering problems. Data collection and pre-processing. What should be the data? Suppose I just want to find out evaporation. My neural network is designed to find out the evaporation, and I have not considered the data of month of May in my entire data series. I have measured all the years, temperature, wind speed, wind velocity, likewise so many causal parameters to have the evapotranspiration, but I don't have the data of May, wherein the maximum temperature is there, and that maximum temperature is basic parameter for evaporation. So your data should be good quality, data should be adequate. Adequate means actually sufficient number of data packets should be there, or data sets should be there. So data collection should be taken care of, and pre-processing should be done. We have not discussed this pre-processing or normalization here, but in depth, whenever you will learn this particular NN course, you will learn the pre-processing processes also. But the domain knowledge is must to know about or to go with the data collection. Data are normalized in the range of -1 to 1, 0.1 to 0.9, and 0 to 1. I will not go in detail with this pre-processing. Okay. Now, initialization of weights. We have discussed the weights. These weights are generally initialized with the random values between -1 to 1. And the number of training samples, obviously, number of data pairs should be greater of number of connection weights. At least this should be greater than the input-output combination of neurons. If the neuron is 1 in an output layer, neurons are there, 5 in a hidden layer, and 5 inputs are there, at least 5 plus 5 plus 1 multiplied by 2, at least you should have 20 data values in your data set. That is means sufficient data also sometimes, but only 20 values cannot train the neural network very efficiently. So the data package should be large also. Large number of training patterns may lead to overfitting sometimes and stuck in the local minima many of the times. To just reduce the problem or evolve the problem of overfitting, cross validation also we can do. Then the stopping criteria. When you are training your neural network, when you are going to stop, whenever the error is reaching up to the minimum value, lowest value, then you should stop the training. Training can be stopped when the error is sufficiently small, and cross validation is used to avoid the overfitting. Validation data set. Network is tested for unseen inputs. Performance of the network judged by correlation coefficient, coefficient of efficiency. These error measures you can use to judge the performance. Traditional error measures, MSE, mean squared error, or RMSE, root mean squared error. These can be used to judge the performance of your developed model. Generally, data division is done in three sets: training, validation, and testing data set. And it should be with a 70% of data should be there. You should be utilized for the training your neural network, and 30% should use for the testing. Out of that 30%, 15% should be for the validation, and 15% should be for the testing one. Likewise, data division, these are advisable. Okay, there are no hard rules for this neural networks that do this and do that. You should learn by your own experience. Unfortunately, there are no fixed guidelines available for the designing of ANN discussed in the foregoing sections that will be. Next few slides deal with the answers to the frequent questions in our mind about designing of ANN. Let us go with that. How does ANN compare with hard computing? See, statistical numerical models we have seen, we have used this. These models a priori require the knowledge. Model orientation is also there. We learn by the definition. Data requirement is very, very high.
Good afternoon, ma'am.
To have the data. And in NN, we see that as it is a soft computing technique, it is soft towards the data. Data error tolerant is also there. Easy in adaptability is also there. Okay, these are some software and references. You can take help of this to go with the designing of neural network. Now, NN model development. I will just give a brief idea about this, how it actually works. To start with, you should decide your particular problem statement, or decide your first problem statement for which you are developing your neural network. Then you should decide. Here the determine word is there, but the better word is decide. Decide the activation function which you are going to use. There are different activation functions. Activation function means actually the transfer functions which we have seen. Training algorithm, we should decide which we are going to use. Then the learning rate, gradient, mean squared error, and the number of epochs. These decisions we need to fix, and we need to develop our neural network. Then load the input data set and the output data set, give that information to the neural network, normalize the data in a particular range, then initialize the weights and biases so that the network will run and first iteration will take place, or the earlier iteration, initial iterations will be there. Then it will calculate the error. Error will be again considered for the reduction. Separate data sets should be utilized for training and testing the data sets. Then once you train the network, use your finalized weights and biases to test that particular network. Testing, if it is done, then you have a final answers with you, and you can say that yes, neural network for one particular problem is developed. Okay, but neural network models, these are of different types. Models are depend upon the time series models, non-time series models. Time series models means which have the time basis actually for the data collection. That means we can consider a stock index, stock market index, that is nothing but a time series parameter. Or rainfall in our hydrology, if we collect 10 years daily rainfall, then we can prepare a time series of daily rainfall values for last 10 years. Or flood discharge, Q today, discharge at time t, that means it is a today's discharge. Qt minus 1, it is nothing but a yesterday's discharge, and Qt minus 2, it is day before yesterday. Likewise, if I put the values in a one particular column, one by one, then it will create a time series of the discharge. So this is a concept of time series. So using time series, you can develop your neural network. Generally in time series, there are two concepts: univariate model and multivariate model. Univariate model means what you are observing right now here, Qt minus 2, Qt minus 1, and Qt. Only one parameter is used, discharge or a stream flow, and its values, today's value, yesterday's value, day before yesterday's value. Likewise, past values, past measured values we will use to forecast the discharge one day ahead, that is Qt plus 1. If this model is developed, then that will be a univariate kind of a model. But what we have learned about the evaporation model, that is again multivariate model, or all cause effect models, or the model which is developed using the causal parameters, that is actually the multivariate kind of a model. Non-time series models are generally cause effect models. Okay, so these are the conceptual some things with a model development. Now let us see one particular model, ANN model for evaporation, how we can develop it. See, whatever we have discussed, my first input I will consider as maximum temperature, maximum humidity, minimum humidity, then maximum daily sunshine, minimum temperature, and last one is wind speed. So these many inputs I have considered to develop a neural network model to know about the evaporation. My final product will be, the output will be evaporation. And these are the hidden neurons, 3 neurons in hidden layer. So this architecture is 1, 2, 3, 4, 5, 6. 6 neurons are there in actually first layer, input layer. 6 is to 3 is to 1. So this is a neural network for evaporation model. Likewise, you can develop a model using this cement, fly ash, coarse sand with a 20%, 10 sand with the size of a coarse aggregate with the 10 size, then water ratio, and you can just model it for the compressive strength and all. Again, the third example, footing length, footing width, embedded depth of the footing, average vertical effective stress of the soil, B2 by ratio, you can consider here friction angle. All these will be the inputs, and the final output will be the bearing capacity. You can develop your neural network for this. Typically, these are the example for civil engineering field. You can observe here, to get the International Roughness Index, RII, actually these are the inputs: annual average precipitation, annual average temperature, freezing index, annual humidity, minimum humidity, maximum humidity, likewise. So these are the causal inputs to map or to get this output of a IIR, roughness index. Likewise, you can develop your own neural network to solve the civil engineering problems. Now I should stop it here. And as I said that the session also involves some applications of this neural network in civil engineering domain. Now I request Professor Londe to go with some applications in his field. Professor Londe, please.
Okay. Thank you, ma'am. Thank you for giving so detailed information about neural network, its working, the algorithms, the types, and I believe that the audience definitely has got an idea about what is this neural network and how it works. So, am I audible to you all? Somebody please respond.
Yes, sir.
Yeah, okay.
Yes.
So after this introduction, now everybody must be wondering that what she has told seems to be highly mathematical and programming and all that. Okay, let us do it. But what are the real applications and where we can use this technology of artificial intelligence or data driven or soft computing called as neural network for our actual practical use? Majoritively, I will discuss about applications in hydrology or water resource engineering, and my colleague Dr. Preeti would discuss in concrete technology as well as in air pollution. But in general, if you people are interested in knowing these applications, right now in front of you are various journals which you should see. From American Society of Civil Engineers, from Science Direct, from Wiley, then Springer. You can see journals like Water Resources Research, Journal of Hydrology, Hydrological Sciences, Hydrological Processes. Nowadays, Indian Society of Hydraulics, our Journal of Hydraulic Engineering is an excellent journal, and it also has many publications on applications of neural networks in hydraulics. There are structural engineering journals, concrete technology journals, environmental journals of ASC, Science Direct, Singer, which will give you a variety of applications of neural network in civil engineering. I will showcase just few of them from hydrology point of view so that you can appreciate the power of this tool. Before I start, let me once again thank the organizers, the entire department, the institute, the university for giving us an opportunity to showcase the neural network applications in front of this audience. So let me start with applications in hydrology. The first one and foremost important for a country like India is stream flow forecasting. Mind well, I'm using the word purposely stream flow forecasting. I'm not using the word that is called as discharge or runoff forecasting. I'm simply using the word stream flow forecasting. Means I'm not going to convert rainfall into runoff. Instead, I am going to work on stream flow, that is the discharge which is flowing in the river at any time. But my purpose over here is what would be discharge flowing in river Narmada at two stations. Narmada purposely I have chosen, you people are from Bhopal, so you know what is the importance of Narmada, and this work has been done way back. The data used is also in 1987 to 1999. Remember that at that time, Sardar Sarovar project was not there. Of course, I will show you the sketch of that. But at that time, this was a completely virgin flow. And it is from the area where you are, MP. And so therefore, I have chosen this particular topic for today's discussion. So the purpose was to forecast stream flow in Narmada at two different locations. What are these two locations? I will just show you. Narmada is the largest west flowing and seventh largest river of India. Its drainage area, it is about 87% of the total drainage area is in MP. And so therefore, once again, I have chosen this topic for you. Total length is given. It has got many important tributaries, so many gauging stations. This is in 2007. Now we are in 2022. This must have been increased by leaps and bounds. So a lot of data is now available, but a similar work, I doubt whether we can do it for the fresh data because now we are having Sardar Sarovar project. Still, on the upstream of the Sardar Sarovar project, we can definitely do that in between two different projects. That is dam 1 and dam 2, because whenever a dam is there, then the flow doesn't remain virgin because the flow is controlled by the dams. But whenever we are working on, say, upstream of a dam, wherever the inflow we are collecting, at that point we can definitely use this technology again. Or if the distance between two dams is very large, in between that, maybe after a certain distance, the flow covers, we can definitely again think about having this kind of technology. So we have chosen Rajghat and Mandleshwar. And our input was only the discharge. Because as I said, I am not going to use any kind of rainfall, especially in this particular problem. Because I am thinking about stream flow. And I'm not doing rainfall runoff model. I am doing stream flow model. So I'm going to use previous values of the discharge which were flowing at the given stations. So just now it has been explained to you that there are models of the kind called as univariate or multivariate. My model is going to be a univariate kind of model where qt plus 1 will be a function of qt, maybe qt minus 1, maybe qt minus 2. So I am just going back. So this time series, this is a time series, univariate time series. So next value is function of previous value. So while deciding the inputs of a neural network for a univariate problem, the first question to be answered is how many these values we have to use. That is the inputs. And this question is answered by 3-4 different ways. When we did this work, I think in 2008 or something like that, the correlation was very much used. First was, of course, trial and error, that you use 2 values, 3 values, 4 values, get the answers, and whatever gives you the best answer is your actually input. But in this particular problem or in this particular publication work, we have used the correlation called as auto correlation. Why auto? Because my variable is the same. So I will try to find out the correlation between this value and this value. Suppose this date is 30, then this date it is 29, 28, 27 likewise. So the discharge at 30 is correlated with the discharge at 29, 28, 27. That is called as autocorrelation. So I will decide that if the autocorrelation value is of this particular range or this is the value of autocorrelation, then I will take those many inputs. And after that, I will not take because that is not influential. Otherwise, we have to go by trial and error, by increasing the number of inputs one by one, that is going back one by one time step. Okay, so these are my inputs, this is my output. Of course, the question remains is, what is my hidden layer and how to design that hidden layer? Okay, let us go one by one in this story. So this is Narmada Basin. As I said, here you won't find any Sardar Sarovar. This is Mandleshwar and this is Rajghat. Okay, distance between them is about 84 kilometers. The river comes from over here, Amarkantak, and then slowly it reaches by various cities, Handia and Hoshangabad, near to that, and then finally it reaches to Surat, and then it reaches to the sea. Okay, so this is the Narmada river. Now, what about data? As I said, 87 to 97, that is 11 years of data. And what is data? Daily average discharge. So it is the value of Q. Nothing else is there. No other hydrologic variable was measured or available. Purposely, the Mandleshwar and Rajghat, at both places, maximum and minimum values, they have been shown to you. Purpose, you can see that, see the range. See the range. That means some people feel that whatever has been shown to you, discussed with you up till now, that there is nothing like a neural network, all this is mathematical jugglery. See, the jugglery cannot be done for this much range, for this variety. From, say, 48,000, 49,000 approximately to 13, you cannot do mathematical jugglery. There has to be some science, some maths behind that, and neural network is the same. And this has been agreed because you can see that this is published in hydrological sciences. Just you can Google in hydrological sciences, you can Google it and you will find out that hydrological sciences is published by IAHS, International Association of Hydrological Sciences, and it is a very, very high quality journal. You can check it out. It is in quartile 1. Its impact factor is very high. Its Chimago factor is also very high. It means that this journal values a lot, and they have accepted the concept of ANN way back in 2010. And all this, whatever I am talking to you now in 2022, after so many years. Now the concept has gone further to deep learning. We are still working in this shallow learning, shallow neural networks, whatever I am explaining you right now. So as I said, first thing first, that should I make model for the entire year or should I make separate models for the month? To answer this question, we plotted all the discharges. It is very clear that from July to October, there are these buildings, large values of discharges as you can see. Okay, and here also you can see that in Rajghat, these are the large values of discharges. But after that, from November to June, the discharges are not much. Or you can say that they are very, very similar. So what we decided, we can have separate monthly model for July, August, September, October. That means these are 4 models for Mandleshwar, 4 models for Rajghat, and one common model for non-monsoon months. That is from year to year. So 4 plus 1 and 4 plus 1. Total 5 models they were developed. A total 10 models, 5 at each location. That is the first decision we took. The second decision was how many inputs, because it is a univariate kind of modeling. Okay, you can see that here these are the 3 inputs. This is the output, right? Q t plus 1. This I will explain, and there is a hidden layer. Hidden layer 5 neurons, they were decided by trial and error. A study was carried out that start with 1 hidden neuron, go beyond 5 also. The results were not improving much after 5, and so we decided that there can be 5. The question was about these 3. So what we did was what is called as auto-correlation analysis. What we found out that the correlation between t plus 1 and t was of the order of 0.97. Then suddenly it decreased to say about 0.6 and about say 0.5 or something like that. I don't remember the exact values. It means that they are having correlation of 0.5, and if you know the concept of correlation, less than 0.7 is again not good. But considering that this is a natural problem, we have decided something. We came to conclusion that if the correlation is less than 0.5 or 0.45, we will not take that as an input. So we stopped at t minus 2. So this is t minus 1 and this is t minus 2. Because if I go for t minus 3, that means once again let me explain. If this is 30th of March, then this is going to be 29th March value, 28th March value, 27th March value, and maybe if I take one more, that is 26th March value, its correlation with the 30th value was not much. And so we stopped at these 3. Using the concept of autocorrelation. Nowadays, there is principal component analysis, there is say AMI, there is of course the beginning, what we should start is always the trial and error. So likewise, there are various techniques now available to decide the number of inputs. We used correlation analysis. So our network is now ready. All the weights are connected. Bias is connected. Now the question is of, this is the architecture. So from the total data, remember it is July. In every July, there will be 31 values. So 31 into, let us say, if it is 11 years, then it is going to be 11 and 331 total. Okay, approximately. Out of that, 70% values they are taken for training, 30% values they are taken for testing. And you can see that everywhere except Mandleshwar July, we require 3 previous values. Mandleshwar July requires 2. Hidden neurons by trial and error. Output neuron t plus 1. Okay, so this is general architecture. You can see that November to June non-monsoon model, and these are all monsoon models. Let us go further. You can see that the results are shown as a scatter plot. This is observed and this is predicted. This is the 45-degree line. If the values they are placed on this 45-degree line, then we can say that it is a perfect matching. But it is very clear that it is not so. Some values are over predicted, some values are under predicted, and R value, the correlation coefficient now don't confuse with the earlier correlation analysis. This is now after the model is developed between the observed and the predicted only for testing. Because in testing, we only give inputs. We asked the neural network to get the outputs. And of course, we do have targets with us to which we compare and then we plot the scatter. No confusion should be there in your mind. So once we do that, it is a scatter plot. R value is 0.75. As I said, for a natural problem like stream flow forecasting in a river, 75 is a very reasonable answer. So I can say that neural network has understood the phenomena of stream flow forecasting, at least in this particular case, if not all. There can be a question in your mind, what is this GP and why it is better? Yeah, GP, genetic programming, another tool which works better to neural networks in many cases. Let us not discuss about that right now. Okay, so these are the points which tell us that here in many cases there is over prediction, and that's why the R value is not that good. It is 0.75. This is the hydrograph. What is hydrograph? These are the values of the discharge versus time. And you can see that this is in the month of October. Excellent predictions. Observed values, they are perfectly matched by the neural network, as you can see. Every up and down has been matched brilliantly by the neural network. That means training is very perfect. That is what I can say. Look at this. Raj, November, June. Now you cannot distinguish between AN and GP and observed. So much matching is there. The peak is also matched very well. So once again, I can say that for Raj, November, June model also, the neural network has understood the underlying phenomena or physics of the stream flow forecasting. Let us see the result of Mandaleshwar, July. It is again small. See the consistency of the model. Earlier in Rajghat, July, the result was 0.75. That is, it is less. Here in Mandaleshwar also, for July, it is less. This is the consistency. That means neural network is not once again mathematical jugglery. It has got very strong mathematical base. It learns. And therefore, in the month of July, the monsoon is onset. There is lot of destabilization or there is lot of, say, variation in the values of the stream flow in the discharge because of onset of monsoon. And so therefore, the network is unable to predict very well because of so much of variations. That can be the reason. The less value of R can be attributed to this because ultimately it learns. It happens to us also. Having biological neural network, this is artificial, so it is bound to have some up and down in the results. Likewise, if you see the values as I said, see here 0.63, 0.65 for ARN as well as GP. Right? This is again 0.75, 0.78. August is also not that good, but from September it has really picked up, as you can see. Same story, September it has picked. That means neural network is very, very consistently giving the answers. For different situations in the month of September, October, August, it is very, very consistent. And for both the places, the results are very consistent. That means, yes, ANN is working well. And this can be used as a tool for getting the flood levels 24 hours ahead at Mandaleshwar and Rajghat both. We can save lots and lots of lives and casualties. That is the advantage of these kind of works. This is the practical importance of these kind of works. And though we do not claim that we are only going to use this technology, we always say that very humbly that this can be a supplementary technique if not alternative. If you want to use finite element based HEGRAS or Mike and you want to find out the values, come on, go ahead, no problem. They do have their different limitations. But if at all, something like neural network, which works on the major data and giving so much of accuracy within no time, Those who work with neural network, they will agree with me that training really requires no time and testing absolutely nothing. And if this much accuracy we can get consistently, why not to use it at least at a supplementary level? This is what is the power of this tool. So this is stream flow forecasting. Let us go to another hydrologic problem, that is evaporation modeling. This is the class A pan evaporation defined in USA. We know how to measure the evaporation. Whatever water you drop or you pour into this, to take it up to the index mark, that much water is evaporated. And evaporations are measured mm per hour or mm per day. And right from our school days, we know that evaporation majoritively depends upon daily solar radiations and the temperatures and the humidities and the wind velocity, which is repeated in any standard book on hydrology. But there is no 100% correct formula, deterministic formula available for evaporation as well as evapotranspiration. All the formulae, they are empirical. And this gives us a scope to come with ANN. Wherever there is randomness involved, wherever there is complexity involved, that is a kind of problem. These kind of problems, they are posed or they pose themselves to neural network for better solutions. These are the candidates for the neural networks to solve. We were having some data. My first student, Dr. N.D. Chowdhury, he was working in Nasik at that time, still working in Nasik. In the Agricultural Institute, they were having a full climatic center and they were having 2 years of data, 2006 and 2007. And this is what they were measuring consistently. And you can see that these are nothing but the values of hydrology and evaporation and the parameters which are influential. Okay, the question was, if I want to develop a neural network, of course, my final answer is going to be pan evaporation, because this is my output. What would be my input? And from where should I start? First question. Second question, if someday this value is not measured, then what should I do? Whether my model will work? Because if it is a finite element based model, or if it is a general formula, which I will show you afterwards, then in the absence of the required data, the formula will not work, but you can calibrate a neural network for the given data. That is the beauty of this technique. With available data also, neural network can work meaningful. And this has been published by International Journal of Hydrology, Science and Technology. Okay, let us see how we took the inputs. We again did the correlation analysis. Just like the previous, it was auto-correlation analysis. This is now cross-correlation analysis. Don't again confuse the analysis which we do after we train the network. That analysis is for the accuracy from observed and predicted. This analysis we are carrying out for selecting the inputs. So there were 6 possible inputs: MHS, humidity, relative humidity, highest, lowest, daily sunshine duration, maximum temperature, minimum temperature, and wind velocity. See the beauty of this technique. This is expressed in meter per second. Temperature, degree centigrade. Temperature, degree centigrade. Daily sunshine duration in hours, and humidity, it is expressed in some different unit. I don't remember. So when I did the cross correlation analysis, I found out that maximum correlation of highest temperature is with the pan evaporation. Common sense, it is like that. Second one is highest humidity. Third one is second humidity, that is the lowest. Fourth one is sunshine duration, and see the wind speed, 0.08. We felt that wind speed should have higher value of correlation. But this happens in case of correlation analysis, because correlation analysis is a linear measure, whereas evaporation is a non-linear process. Still, correlation analysis helps. How? Let us see. So we developed the model. First, we took the best one. That is, we will only use MTX values and get ANN. And get the pan evaporation. Our result was very bad, 0.35. But it gave certain result. And when we added the value of humidity, I got quantum jump in my answer as 0.8. Now, as you can see here, this is the relative humidity, which is smaller. Then this is, I am adding now sunshine duration, minimum temperature, and lastly, see the model where in 1, 2, 3, 4, 5, 6, all 6 are there. My answer is very good. And what else I can prove over here? I can prove that with limited number of inputs also, suppose any of these others are not measured, still with MTX and MHS, I can get 0.8 accuracy. Wonderful. So this proves that ANN can work with limited amount of data, and I can develop all such models such that they can give me meaningful solutions when the entire data is not available to me. All the parameters are not measured. Still, I can calibrate such a model. That is the wonderful aspect of this technology. Okay, then we went further and we did some more permutations, combinations, and as you can see here, final models were MHS, MDS, and MTN. In all the cases, our output is pan evaporation. Remember that, MAP. This is 5 input model. This is again 5 input model. Hidden neurons are 3. Here hidden neurons are 9. And these are general characteristics of the neural network. This is the algorithm, famous LM. Normalization, that is -1 to 1. That means all values, they will be scaled between -1 to 1. The error which you want to minimize is mean squared error. Transfer functions, log sigmoidal and pure lean, means this is a sigmoidal kind of transfer function and this is a linear kind of transfer function between the layers. Data division 70%, 30%, as you can see. So, final values you can see 0.89. Excellent results. Evaporation is a natural process. So, our model is giving 0.89. Let us see what others are doing. See ANN5, ANN6, ANNA, ANNB. This is ANNA and ANNB, ANN5, ANN6. All are written. Normally, people look at it, but you can also look at RMAC. Our RMAC values are also very, very small. Our CE values, they are very high. Our R values, they are also very high compared to Penman Monte, Mayer, Euler, Rover, Prisgard. These are all world famous empirical equations used to measure or used to determine the evaporation or the pan evaporation, and see their values are where they are nowhere near. This proves that ANN is superior compared to these techniques. So what I have to do? I have to measure all this data, calibrate a model, and then I can always give the value of neural networks, the value of pan evaporation. Suppose after 1 or 2 years, I get a feeling that, no, this model is not working well, or the data is changing. What I can do? I can bring back the pan evaporimeter. I will measure the values again, and I can recalibrate my model, because believe me, this model doesn't require much time to train. It is not like final element model that it requires hours and hours. That is the beauty of this technique. So this is computer friendly. This requires less time. This requires less data. This requires, or this is meaningful for the data which is measured, and it has got a solid mathematical background. So therefore, once again, I appeal to all, everywhere, every time, every now and then, that this technique, it can definitely be used as a supplementary technique, if not an alternative technique. This has to be tried and tested at number of places for number of problems. Okay. Further, our Nasik, they are having one data center where there is a hydro project. A World Bank funded project is going on, in which they measure all the values in Maharashtra. I think MP state also would be having such. For that matter, I just forgot to tell you, in the previous Narmada problem, the data was completely supplied by CWC Bhopal. I forgot to mention that. The credit goes to Bhopal division of CWC. Thanks a lot to them. Long back issue, but today I got a chance to say thanks to at least to some Bhopal people for giving us the data. Okay. So, the Maharashtra State Government Office, which is in Nasik, called as Hydro Project, they also calculate this pan evaporation by a mathematical model called as HIMOS. And we tested this especially for the extreme events, 7.36 and 8.08, actually observed values, and see the neural network performance. This is very, very high, so just cut them. HIMOS is in comparison, but it seems that we are beating HIMOS also comprehensively. We are very near, or we are nearer compared to HIMOS to the observed pan evaporation. So this shows that ANN model is beating all of them. Okay. So I will discuss now the last in my kitty, that is rainfall to runoff, because I have discussed with you only stream flow. But many people, they want to have a rainfall to runoff, because this is a very, very practical case. The catchment receives the rainfall, and then maybe on the second or third day, a hydrograph at the outlet, it shows a peak. The rainfall has completely converted into runoff. Until date, there is no 100% deterministic model for converting rainfall to runoff. Of course, there are numerical models in which the Saint-Venant's equation is solved. It is a marching model from, say, upstream to downstream, in which they solve this equation. And these models are like HECRAS or HEC-HMS or Flow2D or Mike 11. Commercial softwares are there, as well as something like HECRAS, which is free. But I am going to develop a neural network model. This is in our own area, that is Pune district, from where we belong to. This basin is called as Krishna Basin. It is again very large basin. We are selecting two tributaries on the river Krishna. One is Bhima, second one is also Bhima. But the streams are different, Kundalika and Indrayani, on which there are these two locations, Budhwad and Nighos, which are there located on these streams. Once again, you can see the values of rainfall. Now here rainfall, that is the difference between the first and this model. I am now going to convert rainfall into runoff. And I am going to use rainfall as my input, as well as discharge also as my input. Because you know, discharge from one place to other place takes some time. We have seen that in the earlier model. And runoff, definitely, it requires time of concentration to reach from one point to other point. So at all these four places, the high values of discharges, they are shown. You can easily understand they are very, very small as compared to Narmada, because this region doesn't receive much rainfall. And that too, compared to Narmada, all these rivers are very, very small. They are rivulets, you can say. Okay. So what is the input? Discharge and rainfall. Somebody's mic is on. Please switch off your mic. Previous day discharge and rainfall. And output next day discharge. You can see here, this is done again by using the cross and autocorrelation. Because you want to find out discharge. So discharge, it will be auto, and rainfall to discharge, it is cross. I hope now you are understanding these things. So, two previous values of discharges and three previous values of rainfall at Budhwar, June. We have not made here non-monsoon because I am converting rainfall to runoff. So, no need of non-monsoon model. Only in 4 to 5 months of monsoon, we need to work out. Every time you will see that here there are now three values of the discharges and three rainfalls, but here there are only two, and here there is only one. And this is done depending upon our correlation analysis, both auto and cross. In Nigose, you can see that this is slightly again different. So the determination of input is a very important exercise in entire neural network modeling, because it can lead you towards excellent answers and it can lead you towards very, very poor answers. So your input selection, and that means your domain knowledge, plays an important role. You should know your subject, your research very well, and then only you can select the inputs very well. Otherwise, your research will be haywire. You will not get good answers. Okay, so these are the inputs. The models are trained by using the same functions. All other things are same, but here that student did some more work and he compared different algorithms. I think Dr. Dikshit explained you these. At least she has given you the names of gradient descent, very, very simplest basic algorithm, then conjugate gradient, CGF, then the back propagation, that is BFG, Newton's algorithm, and lastly the Reservoir. In this work, these four different techniques or models or algorithms, the results of them, they are compared. I think there is again some problem. Somebody is having mic on. Organizers can mute these people. You can mute all. Thank you. So, Budhwar June model, Budhwar July model, especially when the monsoon is onset. You can see that these are the inputs and this is LM, CGF, BFG, GD. See here, architecture is also changing, the hidden neurons especially. Output neurons, input neurons, we cannot change because we want to compare. Comparison has to be done on the same ground, otherwise it is not comparison. Epochs, that means the iterations. I explained you one back propagation iteration. Likewise, there are 14, 10, 16, and you can see the gradient descent is the slowest one. It takes 15,000 epochs. Training testing sake. So LM, CGF, they require less epochs for attaining a very standard low error. In Budhwar, July also, you can see that BFG is 3, this is 21,000. Architecture 6:3:1, same for all. Nigose, I have developed all, but showcasing some of them only. Typical cases with you. Because of the paucity of time. Otherwise, easily we can reach or we can finish it in the evening itself only. Nigose September. Now this is two values of the discharge, three values of the discharge and one previous value of the rainfall. 4:3:1. And there is another model, Nigose September model, maximum discharge shifted to training. Why this is so? There are so many reasons. Let me only tell you that from this data, the value of the highest discharge, which was there in the testing data set, it was shifted to the training data set. There was a reason behind that. We will see, or the benefit of this. It happened that the results of this model, they were easily picked up after we did this exercise. Let me not go into further more details of that. Let me just show you the results. See the results of LM. The high values or the peaks, they are also predicted well. This is the second model of LM. You can see that this is also giving at Budhwar. The results are very good. See the values of scatter. The scatter plot seems to be also well balanced. Along with that, the correlations, they are also very good for LM and BFG. It means that the models are working reasonable. I would say best. Why reasonable? Excellent results. Because this is a natural process, rainfall to runoff. You can see now September 1 and September 2. This is the case. September 1 and September 2. Here you can see that the results of this CGF model, how they are. Okay, so this is September 1 and this is September 2. You can see that still the results are not that good, especially at the peaks. It is not that always neural networks will work well, and I would not also say that. Sometimes there is a problem, but that is the window for us to do some more research into that. So it is necessary that this we should target further, that improving the peak predictions. And there is one more problem, and that problem is improving the prediction accuracy as the forecasting time increases. This is just 1 day ahead. If I go for 2 day ahead, 3 day ahead, it has been found out that the accuracy decreases a bit. Can we maintain the accuracy? This is second problem. You can see that the results over here, all the results, they are at par. However, it seems to be that LM algorithm is working, or these algorithms, they are working far better as compared to GD. For the peaks, you can see that this seems to be working better as compared to all others. For RMAC also, you can see that this seems to be, LM seems to be better compared to others. For C also, this seems to be better or at par at least with others. Always there is a competition between LM, CGF and PFG. However, gradient descent, very primary algorithm, it is always
used in the site or on the site, and which has been accepted overall, is nothing but destructive testing. However, but what is the problem with this destructive testing? That it's very time consuming and means minimum of 28 days. Okay, that's quite some amount of time. And moreover, it's costly also, because a lot of cost goes into materials, the curing, etc. And recycle fine aggregate, natural coarse aggregate 20 mm, 10 mm, and recycle coarse aggregate 20 mm and 10 mm, admixture and water contained being my input parameters. So as you can see here, this is my neural network which was developed. So I had 9 input parameters. Okay. I had one output parameter which is a 28-day strength of concrete, and I had some hidden layers, one hidden layer with some hidden neurons. Now, this number of hidden neurons or the number of hidden layers, they add more amount. The more are the hidden layers, the more are the number of hidden neurons, they add to more degrees of freedom. Okay, so here the number of hidden neurons in the single hidden layer were decided by trial and error methods. Now, let me also put forward this particular point that number of hidden neurons can be actually predicted, can actually be selected depending by various formulas which are being devised by a lot of researchers. But we have worked with all of these formulas, and we came to know that for a specific type of problem where you have a specific type of data, trial and error method seems to work much better. So that was what was selected over here. So the data basically consisted of a lot of experimentation which was done, and some amount of literature was added into, some amount of data from the literature was added to add pattern to the data. Okay, so total data available was 257 instances, that is 257 mixed designs. 70% of the data was used for training and 15% for validation and testing respectively. Now let us see this particular data. As it was highlighted earlier by my colleagues also, that when you use such any type of tool, the basic domain knowledge is of lot of importance. Okay? So you can see here the pattern of the data is also very important. So you can see here the cement content, it was around 235 to 645. That's quite an amount of range. So, and if you see, of course, with other parameters as well, and see the 28-day compressive strength in Newton per mm square, the range of the strength is between 10.319 to 90 Newton per mm square. This is quite a large range. Okay. Now, when the range is large, it of course, it is a challenge to the neural network to give good results even with this larger range, because this larger range also expects you to have that much amount of pattern of data for neural network to learn. Okay. So with this, the model was formulated. Now on this particular part, you can see correlation analysis was done between each of the selected parameter and the output parameter, that is 28-day strength of concrete. This work which we did some time back, here we used correlation analysis, which is a linear measure. Further on, we used AMI, PCA analysis as well to take care of these input parameters, and also to understand what is the non-linear relationship between the parameters, that is the input parameters and the output parameter. Now, this particular activity is important because each of these parameters, they have a non-linear relationship with strength. Like say, for example, water. You increase water, the strength is going to decrease. A non-linear relationship. Okay. So a 3-layered feed-forward backpropagation algorithm was developed, with 9:9:1, as it is shown here also. 9:9:1 was my architecture, and it was still trained till low RMSE, root mean square error, and the transfer function between the first layer and the second layer respectively was log sig and pure line, which is the pure line is a linear measure and log sig is log sigmoidal. And the performance function was mean square error. This was our methodology for development of the model. And just see the results. Okay? Very, very self-explanatory. As we know, or as it was explained by the sir also earlier, the results are not only in the terms of error measures, but it should be also from the visual aspect. Okay? So you can see here the scatter plot, which was drawn between the observed and the predicted values of the strength. And you could see it's quite a balanced scatter. Okay? So all the values, they are surrounding this 45-degree line. So it's a balanced scatter. A slight amount of under predictions, that is fine, which we can further take up as research point. Okay. Now you can see the error measures also. Root mean square error is 5.94. This is also quite less because root mean square error, it actually is very biased towards the higher values. Okay. If the higher values or the residuals, if the errors are very high, then in that case your RMSE value is also very high. Okay. So our objective here is to reduce or to have a model, develop a model which has low RMSE value. You can see a higher value of Nash-Clough efficiency as well. The more it is towards 1, the more better is your model. So 0.86 is quite good. And the most cherry on the cake is this particular figure, which tells you the trend of predicting the strength of concrete. And you can see the observed and ANN values, they are at most in sync with each other. A slight variation can be seen here, which can be taken further and which can be solved by using different types of networks or by changing the number of hidden layers, etc. So this is how your weights and biases actually look. So if you remember, we said that is 9:9:1. So these are the weights and biases for the first input layer to the hidden layer and from hidden layer to the output layer. Okay. Now, this was what was our outcome of this work. So this is a graphical user interface which was being developed. So how this particular interface works? Now, as a developer or as a mixed designer, if you come to me and say that, okay, I have a cement content of say 300, I have natural fine aggregate some X amount, recycle maybe say 0, and some amounts of all these materials. Immediately when I click the submit button, I'll get my 28-day strength. So within a fraction of a second, I'll get this particular data. This saves my 28-day weight as well as cost. So that is what is the beauty of this particular work. Okay. Now this was part 1 where my input parameters were fixed, as I said over here. And these input parameters were fixed because they are the part of my mixed design. So my domain knowledge. But that is not only the thing. Okay. When we are dealing with a mischievous material like concrete, and that too moreover like recycle aggregate concrete, we also have to focus on non-dimensional parameters. Like say for example, you can see on the slide, I'll explain one, right? Like the RR ratio or the replacement ratio. Increase in the replacement of your natural aggregates with recycle aggregates is going to decrease the strength of concrete. Increase in the water to total materials ratio is going to increase 28-day strength is going to increase up to a certain limit. Later it is going to go on increasing. So on and so forth. So this is the one about RR which I was talking about. So if I include these particular non-dimensional parameters, can my neural network give me good results? Okay. So that was what was my second application in the same domain. So as you can see, with my first 9 input parameters, I added off with this 4 non-dimensional parameters as my input parameters. And you can see the results. What I did here was, this is my first model which I explained earlier. And According to the AMI, that is average mutual information, that is the largest nonlinear relationship between a non-dimensional parameter and the output, that is 28 days strength of concrete. I added non-dimensional parameter one by one in the respective model. And I have a model 5-6 in which, with all the input parameters, traditional ones, all the non-dimensional parameters were also added. And I could get a performance of 0.95 of R, that is correlation R. Now, if you can see here, how we can conclude this particular work is that when I considered only the ingredients of concrete in kg per meter cube as my input parameters, my ANN could give me a performance of 0.93, which is pretty good enough. But when non-dimensional was added, it gave me 0.95. There is an increase, no doubt about it. So I would select this. But in case if I do not have these particular non-dimensional parameters, or if they are not measured, or if they are not there with me, in that case, or in spite of that also, I could get a good performing model. That is what is the conclusion of this particular work. Okay. Now, this was again one part. We also would accept this particular fact that material properties also have a large effect on strength of concrete. We all know that. But then you might argue with me stating that you have never considered that. Well, we did that activity as well. So, with a similar type of data, but we also added fly ash based concrete also. We developed another model for that, because we don't want to be biased only to recycle aggregate concrete. Okay? So we used fly ash based concrete also. A separate model was developed for that. And with the materials, ingredients of the materials in kg per meter cube, we also added the most important for our material properties as input parameters, with my output remaining the same as 28 days strength of concrete. You can see here, in this particular recycle aggregate concrete, the material properties which I added was water absorption of recycle aggregate, which, as I explained earlier, this is the most important property, and the water absorption for natural aggregates. These two properties were added over here. And for fly ash based concrete, the specific gravity of 20 mm aggregate and 10 mm aggregate were added. And as well, specific gravity of fine aggregate as well. So these were the properties which were added into the respective models. Okay. Now, once I did that, okay, now these were the set of models which were developed, as I said earlier. So this was my set number 1. 1 model is my model without any properties, and the second one is with the properties, and with only the non-dimensional parameters as well. Okay. Now the ANN was developed with the similar methodology as it was done earlier. Now see the results. Okay. The results for ANN 1-2, that is with the material properties, was 0.88. Okay. Of course, there is a slight reduction. In fact, there is quite an amount of reduction as compared to when the model was developed with only the ingredients in kg per meter cube as my input parameters. Okay. The same pattern I could see for fly ash based concrete also. However, in fly ash based concrete over here, they are at most in sync with each other. So 0.9293 and 9388, they are almost at the similar, they are at par with each other. So this particular table basically concludes that if you have material properties, yes, they can be a very good input parameters, but analyze it and do use it and check the performance. But even if they are not available, nothing to worry. Your raw materials or the raw input parameters can also give you very good results. Okay. So this is the conclusion for this particular work. And of course, here goes our graph, which gives you a visual representation of your results. So just do not pay attention to this green and purple color lines because they are of different tools. So just check out with this blue and red color line, which, as you can see here, they are in sync with each other. You can see a perfect sync over here for fly ash based concrete vis-a-vis to your recycle aggregate. Okay. So this was the first work which was done. Now let us come to another property, that is carbonation. So we know what is carbonation in concrete. Okay, major causes of deterioration. Okay, and carbonation depth is basically being calculated using the fixed second law. We all know about this. However, again, the traditional method is again time consuming, and it's very important that you have an alternative method. So this particular work which I'm presenting right now for this, it is a work which is done in collaboration with University of Lisbon. And here the input parameter selection, there were around 27 parameters, and the parameters were selected using ANOVA technique. And further, ANN and genetic programming was used to predict the carbonation coefficient. Actually, this work is also very important because till this paper was published in 2021, and till 2021 there was no work to the knowledge of the authors that any particular tool was used to predict the carbonation coefficient. Only carbonation depth was done, but carbonation coefficient was not predicted, and so this particular work was very important. Okay, so these were the parameters. As you can see, parameter selection was done using ANOVA, analysis of variance, and there were, of course, 22 parameters with 3 different exposure classes. So that also became very useful. So you can see the mix of the data. Okay, so from clinker percentage to kg per meter cube, 28-day compressive strength, CO2 content, which is the major parameter according to the domain knowledge as well, exposure class, and the most important is the relative humidity. Okay, because as we all know, relative humidity, increase or decrease of relative humidity directly affects the carbonation coefficient. Okay, and my output was carbonation coefficient. Okay, now also with reference to this particular work was divided into 3 parts. Okay, the first part, it consisted of whole sample. Now, what is this whole sample is nothing but when my relative humidity was between 50% to 90%. Okay? Like as I said earlier, when the relative humidity, depending upon the relative humidity and as per the literature, 70% is if the relative humidity is less than 70%, there's a different reaction on the carbonation. There's a different application or reaction to the carbonation coefficient. And if it is more than 70%, there's a different effect. Right? So this particular work was an extension of an earlier work in which set 1 was developed when my relative humidity was between 50% to 90%. That is a whole sample. That's quite an amount of range again. And set 3 and set 4 with relative humidity less than 70% and greater than 70% respectively. That is how the models were designed. Okay? And of course, 70% of the data was used for training and 15% for validation and testing respectively. Now see the results for set 1. Okay? Now as I said, the relative humidity was between 50% to 90%, quite a large amount of range. And see my correlation coefficient, 0.94. That's quite high. Okay, genetic and multiple linear regression also gave very good results, but however, artificial neural network is always the winner. And see the root mean square error. It's 4.55. Now, if you really see the figure below, you can really see here the higher values are not predicted very well by AML. So this can be my further point of research, and that's one of my reason where my root mean square error has increased, which I can take it further for my further research. Now this was about the whole sample, 0.940. So as a modeler or as an investigator, if you come to me and if you ask me that, okay, this is my relative humidity, these are my parameters, you tell me what is going to be my correlation coefficient. Okay? I can give it within a minute of can be seen, which gives you the concentration of the air quality parameters. Now, these air quality parameters are typically SOx, NOx, PM2.5, PM10, and CO. Okay, carbon oxide. Okay. And it also gives you a chart about the AQI. Okay, so air quality index, whether it is good, satisfactory, moderate, etc. Now, this gives you an idea about what is the status of air or how much is the pollution in the air at a present moment. Okay, so if there is going to be any problem, you can take some preventive measures. So, with this particular display charts, this is one of the display chart from Delhi itself. Okay, so this is air quality now. Now means at this present moment. Now, this present moment here was in 2018, that is 29/10/2018. Now it gave me the so these were the two types of models which were developed, and we know what is air quality modeling, air quality index. So as I showed you the display as well. So the models were developed: temporal modeling and cause effect modeling. Now, temporal modeling, we used only the data, okay, of air criteria pollutants, okay, at particular time t, then at particular time t-1, that is yesterday, t-2, that is day before yesterday, and so on and so forth. Okay, and this was done for annual models and for seasonal models. But apart from this, we also made a statement that there are a lot of parameters which affect the air quality pollutants, concentration of air quality pollutants, like the wind speed, relative humidity, etc. And so considering these also became important, and so cause-effect modeling was done. Okay, considering these parameters for annual models and for seasonal models, for 1 day ahead and 2 day ahead. Okay, for better precautionary measures to be taken. So with this effect, with this particular objective, now the data, the work was done for Pune, in which SO2 for T+1, that is for 1 day ahead, that is say for example tomorrow, was predicted with input parameter as a function of SO2T, that is for today, concentration of SO2 for today, SO2 for T-1, that is yesterday, SO2 for T-2, that is day before yesterday. In the similar pattern, the input parameters were selected for NOx and RSPM. Okay. Now, similar way, as 1 day ahead, 2 day ahead forecasting was also being designed. Okay. Now, with this, see the results. Now, these results are from the visual aspects. Now, we can see this particular results where they are a little cumbersome to understand, but you can focus on the dark blue color line and the red color line. Okay, you can see it more clearly for NOx model. You can see the red color line and the blue color line, they are almost in tune with each other. But however, slight, deviations can be seen here, wherein the extreme values are not predicted very well by ANN. Now, this becomes important because this again calls in for the further research. Okay, this is for 1 day ahead. A similar pattern can also be seen for 2 day ahead. Okay, so as you can see here, this red color and blue color line, they are very much in sync with each other. Okay, higher values, yes, they are not predicted very well, but further work was done in this particular area as well. Okay, but still the other days it gives you very good results. Okay, now this was what was the visual representation, but what about the error measures? Now just check out here the winter results and the summer results. Okay, I'll just talk about one of them. Okay, and I'll talk about RMSE for that particular matter. Okay, you see the RMSE values, 9.06, 18.60 and 34. For RSPM it's quite high as compared to others, and this is because of the correct non-prediction of higher values. Your RMSE values also increase. Okay, you can see a similar trend in summer results as well. Okay, now this, you would say that okay, R is 0.3 or 0.56, isn't it less? Yes, it's very much less, but we also have to pay attention that these are the results for 2 day ahead, and this is a natural process. Okay, so this particular results are also quite good. It gives us a lot of confidence for further research. Okay. Now, as we said, for cause-effect modeling, that is relative humidity, wind speed, they are also a part of these particular prediction of SO2, NOx and RSPM. So they were considered, as we can see here, for 1 day ahead prediction. And see the results. Okay. Again, the red color dotted line and the blue color one. The remaining, of course, you can ignore it as of now. Okay. You can see the higher level predictions also, extreme predictions also are done in a better fashion, okay, as compared to the other models. So it's quite a good performing model. Okay. Now, this was all about concentration prediction of SO2, NOx and RSPM. But what about AQI index? Okay, so for AQI index, again, rainfall, temperature difference, vapor pressure, these are all which are going to be your causative parameters. So they were considered as input parameters, and the air quality index for T+1, that is 1 day ahead, was predicted, okay, for winter, summer, monsoon and post-monsoon. Okay. And see the results. This was for Mumbai, okay, for winter, summer, monsoon and post-monsoon. Okay, T+1, this is for T+1. So 0.456573. Okay, Now, if you really, think that in concrete technology, we saw some results which was 0.9, 0.8 and etc. Why these are so less, but you're saying that it's good? The reason being, this is a very, very natural process, which is beyond human control. And so, even if you're having a very good prediction, even if you're having values like 0.63 and 7, it is supposed to be a very good prediction. Okay. See this for Pune also. Okay. And however, when we talk about these particular results, nevertheless to forget that this just depends upon the data. So the more reliable, the more better is your data, the more good or the better will be your predictions all the time. Okay. See for the Nashik also, no, very good results. Okay. Now let's have a visual representation. Now wherever we saw here, winter results were not good, even if it was for Nashik or for Pune or for Mumbai. And that can be reflected over here in our visual representation also, as we can see here. The observed and ANN is not in sync with each other. However, if you see monsoon, yes, it is quite in sync with each other, even for the extreme prediction as well. Okay. Now, this particular work gives you scope for further research. So this was, I can see the results similar to Mumbai. In fact, if you really focus over here also, a sudden drop in the AQI was also being caught by ANN perfectly over here. Okay. So this was for the Nasik as well. Very good predictions. However, higher predictions, yes, there was a problem again. But still, this particular data can be taken care or can be used for further preventive actions. Okay. So here we complete with our applications in ANN. So this particular workshop, now we'll just summarize, and we started with understanding the basics of ANN, how really ANN works, and what is the basic terminologies, what is the basic idea behind neural networks, followed by applications in water resource and in hydrology, followed with applications in concrete technology and air quality. But in all these particular applications, okay, there is always a scope for further research. Okay, the reason being that the input neurons, the output neurons, the hidden layers, hidden neurons, how are we really going to fix them? Okay, as I also made a mention that we have worked on area where the number of hidden neurons, we used a lot of formulas also, and then we came to a conclusion that for our data, trial and error method is the best. Okay, so there are no guidelines as such, and we have to depend upon the data and depend upon our experience. So, can we provide some guidelines for this? What type of transfer functions? Okay, what type of normalization range? -1 or 1, 0 to 1? What type of algorithms? How to stop training of a neural network through iterations, through epochs, or through validation, or through the performance function for a particular data, for a particular application? This needs to be decided. How much should be the data? How much should be the data patterns? Well, these are so many issues. These are some glimpses of issues in ANN modeling, which still has to be addressed. Okay? So, and of course, this leaves us with a lot of scope of research in this particular intriguing field of ANN modeling. So that's all from our team of VIIT over here. So over to you, Aruna ma'am, for any further questions, and we are, all three are here.
Yes, thank you very much, madam. Any questions from the participants? You can ask or you can type in the chat box also. Any questions?
Yes, ma'am. Before that, I'm really sorry to disturb you in between. I'll just send a feedback link in the chat box, and you can just inform the participants to fill this. Just a second, ma'am. Okay, I have pasted the feedback link in the chat box. So I request all the participants to kindly fill the feedback form as well. So over to you, Aruna ma'am.
Yes, any questions from the participants? Yes. Huh. There is one question, madam. How can we decide the number of input layers?
See, there is nothing like, there is only one input layer, and in one input layer there would be number of neurons. Number of neurons, it depends upon the influencing factors. Like in evaporation, we have taken the humidity minimum maximum, then daily sunshine duration, then temperature minimum maximum. Likewise, the influencing parameters, they will be number of neurons. There is nothing like number of input layers. Input layer is only one. Number of neurons in the input layer we have to decide. Then output layer is also one. Number of outputs, they can be more than one. Number of hidden layers, they can be more than one, and which we decide by trial and error. I think I have given your answer.
Yes, sir. Any further questions? Yes. Some research scholars. Any research scholars who are working? Sankar Singh Kushwaha, sir. Yes, Sankar Singh Kushwaha. There is one question, madam, that we have to do coding for this. So it is there is a toolbox in MATLAB also. So
Yes, MATLAB toolbox is there, but it has got limitations because it is a simply a toolbox. Better you write a code in MATLAB because there are many libraries in MATLAB. If you write a code, then it is more flexible than only using the NN tools box. So the research scholars, it is better that they use the actual MATLAB and write a code rather than using any simple available software.
yeah, you have some limitations in
Yeah,
that.
you can use
Yeah.
the libraries and then you can call the libraries in your code and then you can write them.
Yes.
Rather than using any ready-made, because there are always limitations of these kind of ready-made available GUI tools.
Yes, sir. Thank you very much. There is one question from Sachin Singh. Can
Yes,
we predict traffic? Can we
congratulations.
predict traffic? Uh,
Confluences or something like that, maybe. Yes,
uh,
basically, let me tell you that the neural network was used
I'm satisfied
okay.
with this.
So, did you face some queries or something you want to ask to sir? If you have faced some difficulties in your
No, no,
MTech
no, madam,
thesis?
no. Thank you.
So you have done your neural network work in which field?
Madam, for prediction of CBR value of soil.
Okay. So application in your soil mechanics.
Yes, ma'am. I have completed my thesis under Dr. J.P. Tagar, NITRRR.
Okay. Okay. Thank you, Alok.
Thank you,
Any
ma'am.
other? There is one more question, sir. Can we use in construction technology and management data processing with the help of?
Before she answers this, let me tell you that search on Google. There is a paper by myself, Dr. Preeti, and Professor MC Dev of IIT Bombay, only on review of applications of neural network in construction technology and management. We have collected so many papers and we have given comprehensive review.
Yes.
There are many applications in ANN. Ma'am, you can answer.
Yes, as sir rightly said, we have many application in construction technology as well as in concrete technology. Construction management also, we are also working on some of the applications right now. So yes, you can. Yes.
From where we can get the application? I did not get the question. From where can we get the application means what? You can research, you can get applications from various research papers. Search in the journal and you will get variety of applications. There is one more question. Do we have any ANN for predicting MCE, maximum considered earthquake, which a structure will be subjected in its lifetime? This is actually a question to be answered, or this is actually a question for extreme value statistics. So that is a statistical kind of question. If you want to do something with earthquake, then you can as well go for dynamic analysis of the buildings using neural networks. You can go for shear tap corrections in neural networks. So likewise, there are variety of applications in earthquake and structural engineering. But if you are working towards these kind of extreme value problems, then they are better solved by statistics. Okay.
Thank you. Okay.
Any further questions, please?
Yeah.
Okay. Shall we conclude it, ma'am, now?
Yes, madam. We can conclude it. So I am very much thankful to our today's experts, Professor Srinivas Londe and Dr. Pradna Dikshit and Dr. Preeti Kulkarni from Vishwakarma Institute of Technology, Pune, and in very detailed, they have explained the basics of artificial neural network and its applications in various fields of civil engineering like environment and concrete technology, ocean engineering, and we are very much thankful. And I'm also thankful to Professor S.S. Bhadoria, Director of UIT RGPV, Professor S.S. Kushwa, Head of Civil Engineering Department, all the faculty members, and most importantly, the participants who have attended this and enhanced their knowledge in the field of the artificial neural network. Thank you very much.
Thank you.
Thank you.
Thank you very much, madam.
Thank
Hope
you.
your guidance in future also.
Yeah, sure, we are there.
Yeah. So I will send the feedback. So feedbacks link I will send to the participants through their emails also. Okay. Thank you very much.
Thank you.
Thank you. So we are leaving for the meeting. Thank you all the participants for attending the workshop.
We once again appeal all the participants to please respond to the feedback link which is in the chat box so that we can receive your feedback directly. Thank you. Thanks a lot. And tomorrow is the Hindu Navavarsha, Gudi Padwa. So from our side, we congratulate all and we wish everybody a very happy and prosperous and corona-free new year from tomorrow. Thank you. Thanks a lot.
Yes, sir. Thank you very much, and same to you all, sir and madam. Thank you very much. So we are leaving for the meeting. Thank you.